Java Foundations and Memory Management. The Java Virtual Machine as a Runtime Environment. Platform Independence, Advantages, and Disadvantages. Java runs on a virtual software computer rather than directly on the physical processor of your machine, meaning that compiled programs are decoupled from the underlying hardware architecture. This design relies on a uniform intermediate representation that looks identical regardless of whether it is running on a personal computer, a server, or a mobile device. Using this virtual computer approach guarantees that a program written and compiled on one machine will run on any other machine without requiring changes to the code. This achieves what is known as write once, run anywhere. This portability is possible because the intermediate program instructions are not translated into the hardware-specific machine language of any physical processor. Instead, they are translated into a standardized set of instructions designed for the virtual computer, which is custom implemented for each operating system to translate those instructions into the local physical machine language on the fly. For example, if you write a program to calculate student grades, you can compile it on a Windows computer and then execute the compiled file on a macOS laptop or a Linux server. The program will execute with the exact same logical behavior and produce identical output on all three systems without recompiling the source text. The Java Virtual Machine, which acts as a runtime environment by executing compiled programs, provides complete platform independence so that developers do not have to write different code for different operating systems. This environment automatically manages resources via garbage collection, a process that continuously identifies and discards unused memory elements to prevent severe memory leaks. However, this safety and portability come with a disadvantage in the form of execution overhead, meaning that programs may run slightly slower or require more processor power than programs compiled directly for the physical hardware. The compilation process, source code, bytecode, just-in-time compiler, and machine code. The transition from human-written instructions to execution on physical hardware involves a two-stage translation process. First, the developer writes instructions in a human-readable language, which is then translated into a machine-independent intermediate format, and finally, this intermediate format is converted into physical machine instructions during execution. This dual-stage translation process combines the safety and verification of static compilation with the runtime performance optimization of dynamic execution. This separation of compilation and execution allows the compiler to detect syntax and typing errors before the program is run, while the execution environment can optimize the instructions specifically for the hardware configuration of the computer currently running the program. For instance, when a developer runs the compiler tool javac on a file named helloworld.java, the tool verifies the correctness of the code and generates a new file named helloworld class containing the intermediate instructions, which is then loaded and executed by the Java execution tool. The raw text written by a programmer is known as source code, which is saved in files ending with the extension .java. This text is processed by a tool called javac, which serves as the compiler that translates the human-readable text into a machine-independent format called bytecode. This intermediate bytecode is stored in a .class file, which is then read by the virtual machine at runtime. To speed up execution, a component called the just-in-time compiler translates sections of this bytecode into native machine code directly understood by the physical processor during execution. This process supports dynamic binding, which resolves method calls at runtime, whereas static binding resolves functions before execution, as seen in older languages. Imperative versus object-oriented programming concepts in Java. Java is designed to support multiple programming styles, allowing developers to write programs using step-by-step procedures or by defining structures that model real-world concepts. This flexibility means that programmers can choose the most appropriate tool for a given task, whether it is a simple calculation or a large enterprise application. Object-oriented concepts are vastly superior for managing large and complex software systems, while imperative concepts remain highly effective for small, self-contained algorithms and mathematical calculations. Object-oriented design groups data and the actions that can be performed on that data together, which makes the code easier to maintain, modify, and reuse without breaking other parts of the program, whereas imperative design separates data from functions, leading to disorganized code as the project grows. For example, A simple statistics utility that calculates the average value of a list of numbers is best written as an imperative procedure that takes an array as input and returns a single decimal number, whereas a university management system with students, professors, and courses is far better modeled using distinct objects that interact with one another. Java supports imperative programming, a style where the developer defines step-by-step instructions and updates variables, as well as object-oriented programming, which is a paradigm that structures programs around objects that contain both data and behavior. In the imperative style, you often use a static method, which belongs to the class itself and does not require an object to be instantiated, promoting basic modular programming. Conversely, the object-oriented style relies on a class, which serves as a blueprint, to instantiate an object in memory. This approach enforces encapsulation by hiding internal data from external access, allows reuse through inheritance by specializing parent classes, and establishes contracts via an interface that defines method signatures without implementing them. Data types. Primitive data types versus complex reference types. Java distinguishes between simple, raw values and complex, multi-part objects to manage memory and execution speed efficiently. Simple values are stored directly in a compact format, while complex objects are accessed through their location in memory, which requires a separate reference. Separating simple values from complex objects allows the computer to perform basic mathematical operations at maximum hardware speed while still supporting sophisticated, extensible data structures. Simple values have a fixed, unchangeable size in memory and are stored in the fastest access area of the computer, whereas complex objects can grow in size and must be allocated in a flexible memory area, meaning they require a pointer lookup step to access their content. For example, if you declare an integer variable to store the age of a person, the computer stores the numeric value 39 directly in the variable, but if you declare a variable for the name of that person, the computer stores a memory address that points to a text object containing the letters of the name. A basic category of values is the primitive data type, also referred to as value types, which include numeric representations such as byte, short, int, long, float, and double, along with the character type char and the logical type boolean. On the other hand, complex reference types, which represent objects and arrays, are accessed using reference variables that hold the memory address of the actual data. These types include strings, which represent sequences of characters and are immutable because their value cannot be changed once created, as well as wrapper types such as integer and double, which encapsulate primitive values inside objects. The compiler simplifies the transition between these two domains through autoboxing, which automatically converts a primitive value into its corresponding wrapper object, and auto-unboxing, which extracts the primitive value from the wrapper object when needed. Memory areas, the stack versus the heap. Java organizes the computer's memory into two distinct areas to manage the active execution of your program and the storage of all created objects. One area is highly structured and tied directly to the currently running methods, while the other is a large, flexible pool that holds all dynamic objects. Automatic memory management in Java prevents severe bugs such as memory leaks and dangling pointers that plague systems' programming languages. The virtual machine automatically tracks which objects are still in use by analyzing whether they can be reached from the active execution frames, and automatically reclaims the memory of any unreachable objects without any manual intervention from the programmer. For example, when a method creates a new point object and then finishes executing, the variable pointing to that object is removed from the stack, leaving the point object on the heap with no active references, which allows the automatic reclamation system to safely delete it from memory. The stack is a structured memory area that stores a stack frame for every active method call, containing local variables and parameter values that only exist while the method is executing. In contrast, the heap is a large, unorganized memory area used for object allocation whenever a new object is created. Since Java references are safe pointers that cannot be manipulated mathematically, the virtual machine can employ a garbage collector running a mark and sweep algorithm to safely identify and deallocate unreferenced objects. If a reference variable does not point to any object, it holds a null reference, which represents an invalid address and will trigger a null pointer exception if a program attempts to call a method on it. Arrays as a data structure, one-dimensional and multidimensional arrays in memory. An array is a collection of elements of the same type stored together, but in Java, every array is treated as a fully fledged object. This means that arrays are created dynamically and are managed in the same flexible memory area as other objects. Java's array implementation prevents security vulnerabilities and program crashes caused by accessing memory outside the allocated array boundaries. Every array object stores its own size alongside its data, and the execution environment checks every single access index against this size, immediately halting execution with an error if the index is negative or greater than or equal to the size of the array. For instance, if you create an array to store 5 decimal numbers, the system allocates an object on the heap that stores the length 5 followed by space for the 5 numbers, and any attempt to write to the index 5 or higher will immediately cause the program to stop. A one-dimensional array is a contiguous sequence of elements stored as a single object on the heap, whereas a multidimensional array is represented in memory as an array of array references, meaning it is a chain of reference variables pointing to other arrays. When an array is created, the system performs a heap allocation and returns the starting address, which is stored in an array reference variable. You can query the size of an array using its length attribute, which the virtual machine uses to prevent any out-of-bounds access errors. When copying arrays, a simple assignment copies only the reference, meaning both variables point to the same array in memory, so developers must use dedicated loops or system functions to copy the actual values and create a separate array object. Control flow structures, decision branches, and loops. Programs must be able to choose different execution paths based on conditions and repeat blocks of instructions until a goal is met. Java provides dedicated structures that allow you to direct the computer's path through your code based on logical tests. Selecting the most specific control structure for a given task dramatically improves code readability and reduces the risk of logic errors. Using specialized structures like multi-way branches or count-controlled repetition clearly communicates the programmer's intent to both the compiler and other developers, whereas using generic conditional loops for every task increases the risk of creating infinite execution loops. For example, if you need to perform an operation exactly 5 times, you should use a structure that automatically manages a counter variable, but if you need to choose an action based on a single character input, you should use a structure that jumps directly to the matching case. Java provides control flow structures, which determine the execution order of statements, consisting of decision branches that choose paths and loops that repeat execution. A basic branch is the if statement, which evaluates a Boolean expression to decide whether to run a block of code, while the switch statement offers an efficient way to select among multiple discrete values of a variable. In a switch block, developers must be careful about case fall-through, which occurs when execution continues into the next case, and must use a break statement to exit the block. For repetition, the for loop is used when the number of iterations is known beforehand, whereas the while loop evaluates its condition before each iteration, and the do-while loop evaluates its condition after each iteration, ensuring that the loop body runs at least once. Principle of modularization, separation of client, application programming interface, and implementation. The principle of modularization is based on the idea of dividing a large computer program into smaller, independent building blocks. By doing so, developers can understand, test, and maintain code much more easily because they do not have to grasp the entire system at once. Dividing software into independent parts ensures that changes to one section do not unexpectedly break other parts of the program. This robustness is achieved because the separate sections interact only through a strictly defined boundary, which prevents the inner workings of one section from being accessed or modified directly by another. For instance, if we consider a statistical helper library, we can create a specific file that calculates statistical values such as the average or variance. A separate main program can then call these calculation methods without ever knowing how the internal algorithms actually compute the final values. In the language of academic computer science, we refer to the module that uses the provided functionality as the client. The strictly defined boundary that acts as a formal contract between different parts of the system is called the application programming interface, which is commonly known by its abbreviation as the API. The actual code that performs the work and contains the concrete Java instructions is called the implementation. By separating these components, we establish a clean separation of concerns, which ensures compatibility and allows developers to swap the underlying implementation without affecting the client. class variables and static methods versus instance variables and instance methods. When writing code, we must decide whether certain data and actions belong to the template of a class itself or to the individual objects we create from that template. Understanding this difference is essential for managing memory and ensuring that different parts of our program can share information correctly. Static elements are shared across the entire program and do not require us to create an individual object to use them. This is because static elements are associated directly with the class template rather than with a specific instance, meaning they are loaded into memory once and persist throughout the entire lifecycle of the application. For example, a mathematical library class might define a constant value for the maximum postal code, which remains the same for every address we process, or a helper method to parse a string into an integer, which simply acts on its input and does not depend on any unique object state. Variables defined with a static modifier are called class variables, and they are initialized when the class is loaded by the virtual machine. Methods declared with a static modifier are called static methods, and they can be invoked directly using the class name followed by the dot operator. In contrast, non-static variables are known as instance variables or object variables, which represent the unique state of a specific object. Non-static actions are referred to as instance methods, and they can only be called on a concrete object because they have direct access to that specific object's instance variables through the implicit current object reference known as this. Method overloading within a class and the signature rules. Sometimes we want to perform the same general action but with different types of input data. Method overloading allows us to reuse the same name for multiple methods in a class, making our code much more readable and intuitive to use. We can define multiple methods with the exact same name inside a single class as long as the compiler can distinguish between them based on their parameters. The compiler differentiates overloaded methods by examining the specific types, number, and sequence of the parameters provided during a call, which allows it to resolve the correct method at compile time. For instance, we can write 3 different averaging methods inside a single utility class, where the first method calculates the average of 2 integers, the second method calculates the average of 2 double-precision floating-point numbers, and the third method calculates the average of 3 double-precision floating-point numbers. The unique identifier that Java uses to distinguish one method from another is called the method signature, which is composed of the method name and the ordered list of parameter types. When we define multiple methods with the same name but different signatures, we are performing method overloading, which is a form of ad hoc polymorphism. It is important to note that the return type of a method is not part of the signature, meaning we cannot overload a method simply by changing its return type. Furthermore, when an overloaded method is called, the compiler performs static binding to determine the most specific matching signature based on the compile time types of the arguments. Namespaces, packages, declaration, import statements, and static imports. As software grows larger, we often run into situations where different developers choose the same names for their classes. To prevent these names from clashing, we need a way to group related classes and give them unique, structured names. Organizing classes into distinct folders on the hard drive allows us to use identical class names in different parts of a project without any conflicts. This structure works because the folder path is treated as part of the full name of the class, creating unique pathways that the compiler can easily tell apart. For example, we can have a class named average inside a folder named 1, and another class also named average inside a folder named 2, and the compiler will compile both successfully because their full pathways are completely distinct. These structured namespaces in Java are called packages, and we declare them at the very top of our source file using the package keyword followed by the package name. To use a class from another package, we must either write out its fully qualified name or include an import statement at the beginning of our file to make the short name directly available. Fundamentally, classes in the implicit language package called java.lang are always visible and do not require import statements. Additionally, Java supports static imports, which are declared using the import static keywords and allow us to use static methods or class variables directly without prefixing them with their class name. Visibility modifiers on module level. When we build software components, we must decide which parts of our code should be accessible to other developers and which parts should remain hidden. Controlling access to our code ensures that the internal data of our components cannot be modified in harmful or unexpected ways. Hiding the internal variables of a class and allowing access only through public methods protects the integrity of our data. This encapsulation prevents clients from becoming dependent on specific implementation details, allowing us to change the internal structure of our class later without breaking any external code. For instance, in a class representing a person, we can make the first name and surname variables completely inaccessible from the outside, while providing public methods to safely read or update these values. The keywords we use to define these access restrictions are called visibility modifiers or access modifiers. The public modifier makes a class, method, or variable accessible from any other class in any package. The private modifier restricts access strictly to the declaring class, which is vital for hiding sensitive implementation details. The protected modifier allows access within the same package and also to subclasses in other packages through inheritance. Finally, if we omit any modifier, Java applies the default package visibility, also known as package private visibility, which restricts access solely to classes within the exact same package. Scope of local variables. Variables that we use temporarily to perform a calculation inside a single method do not need to exist forever. Limiting the lifetime of these variables makes our program safer and prevents us from accidentally using old, outdated data. A variable created inside a specific block of code becomes completely invalid and inaccessible once that block is finished. This occurs because the virtual machine automatically discards the variable from memory when the execution leaves the block where the variable was declared. For example, if we declare a loop counter variable inside a loop block, we can use that variable to access elements of an array, but if we try to read or modify that variable after the loop is finished, the compiler will produce an error because the variable no longer exists. The region of program text where a variable can be accessed by its name is called its scope. For variables declared inside a method, which are known as local variables, the scope begins exactly at the point of declaration and extends to the end of the enclosing block marked by the closing curly brace. Unlike some other languages, Java strictly forbids local variable redeclaration, meaning we cannot declare another local variable with the exact same name within the same scope or any nested blocks. As a best practice in software engineering, developers should always declare local variables in the narrowest possible scope to limit their visibility and lifetime. Classes as blueprints and objects as instances. Object-oriented programming gives developers the ability to define their own custom data types in order to represent and transform abstract models of the real world in computer programs. We achieve this by creating a general template that defines both the structure of the data and the set of actions that can be performed on that data. Creating a dedicated template is essential because it allows us to manufacture multiple distinct entities that represent unique individuals within our system. This is because a general blueprint merely defines the available properties, whereas each individual entity created from it contains its own unique data and occupies its own separate space in the computer memory. For example, we can define a general template for a person, and then use it to create a specific person named Carlo Pedersoli who has his own distinct forename and surname variables. In the formal concepts of advanced programming, the general template we write is called a class. The concrete entities we construct from this class are called objects, which are also referred to as instances of that class. When we create a new object, the Java virtual machine reserves a dedicated block of memory for its data on the heap, and this object remains uniquely identifiable throughout its entire lifetime, for example by its initial memory address. Encapsulation and data encapsulation using getter and setter methods. When we design software components, it is a highly desirable practice to protect the internal data of our objects from being accessed or modified directly by external code. This restriction prevents other parts of the program from corrupting the internal state of our components in harmful or unexpected ways. Restricting direct access to internal variables is highly beneficial because it prevents user code from becoming tightly coupled to the specific way we choose to store our data. This independence ensures that we can completely alter our internal data structures or algorithms later without breaking any of the external client code that uses our component. For instance, in a component representing a person, we can make the forename and surname variables completely inaccessible from the outside, which allows us to add a validation check that prevents anyone from setting a name to a null reference. This protective design principle is known as encapsulation or information hiding, which works by hiding the internal representation of an abstract data type. To implement this in Java, we declare our object variables with a private visibility modifier and provide public access methods, which are specifically known as getter methods for reading the data and setter methods for writing the data. This structure is a core convention for creating clean data containers called Java beans or plain old Java objects, where all variables are kept private and any modifications are safely filtered through these public access methods. Constructors, the default constructor, overloaded constructors, and constructor chaining. When we create a new object, we need a reliable mechanism to set up its initial state and assign valid starting values to its variables right at the moment of its creation. This setup process must run automatically so that we do not accidentally attempt to use objects that contain incomplete or uninitialized data. Providing multiple different setup options makes our components much more flexible and easier to integrate into different parts of our software. This is because different scenarios require different initial information, and having multiple setup methods allows us to handle all these situations cleanly while reusing our initialization logic to avoid duplicate code. For example, we can choose to set up a person object with no initial name details, or we can choose to pass a specific forename and surname immediately, or we can even set it up by copying the details directly from another already existing person object. The special methods we write to create and initialize new objects are called constructors, which are invoked using the new operator, have no return type, and must share the exact name of the class. If we do not define any constructor in our class, the compiler automatically inserts a parameterless, empty constructor which is known as a default constructor. When we define multiple constructors with different parameters, we are using overloaded constructors, and we can link them together to reuse our setup logic by performing constructor chaining, which is achieved by calling another constructor in the same class using the special this call. The this reference to the current object. Within our class definitions, we frequently need to write methods and constructors that refer directly to the specific object that is currently executing the code. We require a clear and unambiguous way to point to the variables of the active object, especially when other variables in the immediate vicinity share the exact same names. Having a precise way to refer to the active object prevents subtle programming bugs where different variables shadow one another. This is because when a temporary method parameter has the exact same name as a variable belonging to the object, the temporary parameter hides the object variable, which can lead to accidental mistakes where we write data to a temporary variable instead of saving it permanently. For instance, in a constructor for a complex number, we use the parameter names to accept the real and imaginary parts, and we must make sure we assign these values to the actual object variables rather than just overwriting the parameters. In Java, we resolve this naming conflict by using the keyword known as the this reference, which represents a reference to the current, active object in execution. By prefixing our variables with the this reference followed by the dot operator, we tell the compiler that we want to access the instance variables of the current object rather than any temporary local variables. This reference is also used to perform constructor chaining by invoking other constructors of the current class, or to pass the current object as an argument to other methods. Immutable versus mutable data types. When we design our own data types, we must decide whether the value of an object can be modified after it has been created, or if it must remain completely constant throughout its entire lifetime. This decision has major implications for how safely and easily we can share objects between different parts of our program. Using objects that cannot be changed after creation makes our software much more robust because it completely eliminates unexpected side effects. This safety exists because we can freely pass these constant objects to other methods without any risk that those methods might secretly modify our data. For example, if we create an immutable color object representing gold, its color values can never be altered, whereas if we share a mutable point object between two variables, modifying the coordinates through one variable will instantly change the coordinates seen by the other variable because both point to the exact same object in memory. Data types that do not allow their values or internal state to be altered after they are constructed are called immutable types, with prominent examples in the Java standard library being the string class, the color class, and the standard numeric wrapper types such as integer. Conversely, data types that explicitly allow their internal values to be modified are called mutable types, with common examples being the point class and the picture class. It is worth noting that certain operations, such as generating a consistent hashcode, are not supported for mutable types because their values can change over time. Object comparison, object identity versus content equality. Comparing objects in a computer program requires us to make a clear distinction between two fundamentally different types of equality. We must be able to determine whether two variables point to the exact same physical location in memory, or if they point to different locations that happen to hold identical data. Making this distinction is vital because treating different objects with identical data as the exact same object can lead to major logical errors in our programs. This is because two objects can exist at completely different addresses in the computer memory while still representing the same conceptual value. For example, if we create two different point objects that both represent the coordinate 10,10, a memory location check will tell us they are not the same, but a structural check will tell us they are indeed equal because their coordinates are identical. In Java, checking whether two variables point to the exact same memory address is called checking for object identity, which is performed using the double equals comparison operator. To check whether the internal values of two objects are structurally identical, we use the equals method, which measures content equality or state equality. While the default implementation of the equals method inherited from the base object class simply performs a reference comparison using the double equals operator, developers must override this method in their custom classes to implement a proper, element-wise state comparison. String pooling. Text is one of the most common types of data used in software development, and storing the exact same words multiple times in different parts of the memory would waste a massive amount of system resources. To prevent this waste, Java automatically reuse a single copy of a text value whenever we write the same text directly in our code. This automatic reuse strategy is highly effective because it significantly reduces the memory footprint of our programs and speeds up text processing. This efficiency is achieved because the virtual machine keeps a central registry for text values, ensuring that identical text literals share the exact same memory location. For example, if we declare two different variables in our program and assign the exact same text literal containing the letters A, B, and C to both, they will both point to the exact same address, whereas if we explicitly force the creation of a new text object using the new operator, they will reside at different addresses. This optimization technique is known as string pooling, and the dedicated memory region managed by the virtual machine is called the string pool. The process of storing only a single copy of each unique text value in this pool is called interning, which applies automatically to all string literals. Because of string pooling, comparing two string literals with the double equals operator can sometimes return true, but to ensure our code is safe and robust, we must always compare text values using the equals method. Handling and checking null references and avoiding the null pointer exception. Sometimes we need a way to represent the absence of a value, such as a variable that has not been assigned to any real object yet. However, we must be extremely careful when working with these empty variables, because trying to perform actions on a variable that does not point to anything will cause our program to crash instantly. Performing an explicit check before using a variable is absolutely essential to prevent our programs from crashing unexpectedly when values are missing. This is because the computer cannot execute an action on a non-existent object, so we must detect this empty state early and handle it gracefully as a special case. For example, if we have a point variable that is empty, trying to set its coordinates will cause a severe runtime error, but we can prevent this crash by wrapping the coordinate setup code in a simple condition that only runs if the variable actually contains a valid point. The special value used to represent an unassigned or empty state is called a null reference, which can be assigned to any reference variable. If we attempt to invoke a method or access data through a variable that contains this empty value, the virtual machine will throw a runtime error called a null pointer exception. To avoid this exception, we must perform a null check using the double equals or not equals operators, allowing us to safely branch our control flow depending on whether we have a valid object reference or a null reference. Automatic memory management, garbage collection, and the mark and sweep algorithm. When we create objects in our programs, they occupy space in the computer memory. If we keep creating new objects without ever cleaning up the old ones that we no longer need, our computer will eventually run completely out of memory and our program will fail. Letting the system automatically clean up unused memory is a massive advantage because it relieves developers from the burden of manually tracking every single byte of allocated space. This automation is vital because manual memory cleanup is extremely error-prone and frequently leads to severe bugs where memory is either forgotten and wasted, or freed too early while it is still in use. For instance, in a program that constantly creates temporary point objects during a calculation, we can simply discard our references to those points when we are done, and the system will safely reclaim the memory on the heap without any manual intervention from us. This automated memory management system is called garbage collection, and the component of the virtual machine that performs this work is the garbage collector. This process prevents severe memory waste known as memory leaks, although it is computationally intensive. A fundamental algorithm used for this cleanup is the mark and sweep algorithm, which works by first traversing all active references starting from the execution stack to mark all reachable objects on the heap, and then sweeping through the heap to safely deallocate and reclaim the space occupied by all unmarked, orphaned objects that can no longer be reached. Generalization and specialization class inheritance using extends. When we design software, we frequently notice that different data types share identical properties and behaviors. Rather than duplicating the same program code repeatedly, we can create a foundational blueprint that holds the common elements and then derive more specific blueprints from it. Deriving specific blueprints from a foundational one drastically reduces code duplication and simplifies future maintenance. This improvement occurs because any shared data or behavior only needs to be written and tested once in the foundational blueprint, and every derived blueprint automatically adopts these elements without any additional programming effort. For example, if we write a foundational blueprint for a person that includes variables for a forename and a surname, we can construct a specific blueprint for an actor that automatically possesses these two name variables while only adding a new variable for a stage name. In the formal language of computer science, this concept is called inheritance, which is a core mechanism for reusing code. The architectural process of moving shared attributes up into a common blueprint is known as generalization, whereas the creation of a narrower blueprint is called specialization. The newly derived blueprint is referred to as the subclass or child class, and the foundational blueprint it extends is known as the superclass or parent class. We implement this in our code by adding the keyword extends to the class definition, which instructs the compiler to pass all visible properties and actions from the parent down to the child. The Substitution Principle. When we connect general and specific blueprints, we need an absolute guarantee that the specific versions can seamlessly take the place of the general ones. This means that whenever a specific part of our program requires a general item, it must also flawlessly accept any specific item derived from it. Allowing specific items to substitute general items makes software incredibly adaptable and open to future expansions. This adaptability is guaranteed because the specific item inherently possesses all the mandatory properties and actions of the general item, ensuring that the surrounding system can interact with it using the exact same commands. For instance, if a program routine is designed to process a person object and print out the forename and surname, we can safely provide an actor object to this routine because the actor is guaranteed to contain the exact same forename and surname variables. This fundamental rule is formally known as the Substitution Principle, or the Liskov Substitution Principle, named after the computer scientist Barbara Liskov. It dictates that an object of a superclass can always be seamlessly replaced by an object of a subclass. Because this principle holds true, object-oriented languages support polymorphism, which means that a single variable defined with a superclass type can point to objects of many different subclass types during the actual execution of the program. Method overriding versus method overloading. Sometimes a derived blueprint inherits an action from its parent, but the derived version needs to perform this action in a customized way. We require a way to replace the inherited action with a new tailored version that perfectly fits the specific needs of the derived blueprint. Replacing an inherited action with a tailored one ensures that specific items can keep the same external command structure while fundamentally changing their internal execution. This works smoothly because the compiler identifies that the derived item has supplied its own exact match for the inherited command, and it will subsequently prioritize this specific version over the general one provided by the parent. For example, if a general person blueprint provides an action to generate a text description containing just the forename and surname, the specific actor blueprint can replace this exact action to generate a description that also includes the stage name. When a subclass replaces an action from its superclass by providing a method with the exact same name and the exact same parameter list, this is called method overriding. It is critically important to distinguish this from method overloading, which happens when we write multiple methods with the exact same name but completely different parameters within a single class. Method overriding replaces an inherited behavior entirely, whereas method overloading merely creates additional differently parameterized variations of a behavior. The universal base class object and overriding toString equals and hashCode. In the programming environment, every single blueprint we create is automatically woven into one massive, overarching family tree. This means that absolutely every item in the system shares a single ultimate ancestor and automatically receives a basic set of fundamental actions from the moment it is created. Providing a single common ancestor for all items guarantees that the system can always interact with any unknown item using a standard set of fundamental commands. This standardization is achieved because the compiler silently links every new blueprint to this universal ancestor, ensuring that basic operations for comparing or describing items are always present even if the programmer never writes them. For instance, if we create a completely empty blueprint for a university course and then instantiate a new course item, we can still instruct that item to provide a text description of itself because it inherited this specific ability directly from the universal ancestor. This universal base class is named object and it resides in the core language package. Because every class implicitly extends object, they all inherit standard methods such as the toString method, which generates a text representation of the item, and the equals method, which checks if two items are identical. They also inherit the hashCode method, which calculates a unique numeric value for the item. Developers are strongly advised to perform method overriding on these specific methods in their custom classes to provide readable text descriptions and accurate content equality checks instead of relying on the default memory address comparisons. Constructor calls in inheritance hierarchies using super. When we construct a new specific item, we must ensure that all the internal data it inherited from its parent is properly set up before we initialize its own specific data. The specific item needs a reliable way to trigger the setup routine of its parent blueprint during its own creation phase. Forcing the specific item to call the parent setup routine guarantees that no inherited variables are left uninitialized or in an invalid state. This initialization sequence is necessary because the specific blueprint often does not have direct access to the hidden internal variables of the parent, so it must strictly rely on the parent to establish its own secure state. For example, when creating a new actor item, the actor setup routine must first pass the forename and surname to the person setup routine to securely store those names, and only after that is completed can it proceed to save the stage name in its own specific variable. The setup routines responsible for this initialization are called constructors. In an inheritance hierarchy, a subclass constructor must invoke a superclass constructor to initialize the inherited state, which is done using the keyword super followed by the required arguments. If a developer does not explicitly write this call, the compiler will automatically insert a hidden call to the parameterless default constructor of the superclass at the very beginning of the subclass constructor to ensure the hierarchy is fully initialized. Dynamic binding at runtime. When a variable is defined using a general type, but actually points to a specific customized item, the program must decide which version of a shared action to execute. The system intelligently waits until the exact moment the action is requested to check which specific item is truly sitting in the memory. Waiting until the last possible moment to link the command to the code ensures that the system always executes the most specific and correct behavior for the item at hand. This delayed decision works because the execution engine completely ignores the general type of the variable and instead inspects the concrete item loaded in the memory during the actual run, routing the command directly to that item. For instance, if we have a variable defined as a general person but we assign a specific actor object to it and then ask the variable for its text description, the program will execute the customized description method of the actor rather than the general description method of the person. This architectural mechanism is called dynamic binding, which is also frequently referred to as late binding or dynamic dispatch. It dictates that the connection between a method call and the actual method implementation is established at runtime based on the concrete type of the object, rather than at compile time based on the static type of the reference variable. Dynamic binding is the fundamental engine that makes polymorphism function correctly because it allows a single method call to produce entirely different behaviors depending on the actual objects processed during execution. Abstract classes and abstract methods. Sometimes we want to create a general blueprint that defines a common action, but the general concept is too vague to actually perform that action itself. Instead of writing a meaningless placeholder action, we can simply declare that the action is mandatory and force all specific child blueprints to provide their own exact implementations. Forcing child blueprints to provide an implementation ensures that every specific item knows exactly how to perform the action while strictly preventing the creation of vague, useless parent items. This restriction is effective because the compiler strictly prohibits creating items from the vague parent blueprint, and it will actively refuse to compile any child blueprint that fails to supply the required concrete action. For example, we might create a general blueprint for a geometric shape that declares an action to calculate its area, but since a general shape has no specific formula, we leave it blank and force specific blueprints like circles and rectangles to supply their actual mathematical formulas. A blueprint that cannot be instantiated and is designed solely to be inherited from is called an abstract class, which we define using the abstract keyword. The blank mandatory actions it declares are called abstract methods, and they consist only of a signature without any method body. When a concrete subclass inherits from an abstract class, it is strictly obligated by the compiler to implement all inherited abstract methods, thereby ensuring that the complete functional contract is fulfilled. Interfaces as functional contracts. In large software projects, we often need to guarantee that completely unrelated items can all perform a specific set of actions, even if they share no common upper blueprint. We can create a pure stand-alone contract that simply lists the required actions without providing any internal data or implementations. Using pure functional contracts allows us to treat completely different items in the exact same way as long as they all formally agree to fulfill the required actions. This standardization is powerful because the contract acts as a strict structural checklist, ensuring that any blueprint signing the contract must write the actual code for all the listed actions, which guarantees to the system that the item can be interacted with safely. For instance, we can create a contract for sorting items that simply requires an action to compare two objects. Then both a university course blueprint and a complex number blueprint can sign this contract and provide their own comparison rules, allowing a single sorting machine to process both courses and numbers effortlessly. In the Java programming language, these pure functional contracts are called interfaces. An interface defines a distinct abstract type that typically contains only public abstract method declarations without any method bodies. When a class formally agrees to fulfill this contract, we say the class implements the interface, which forces the class to provide concrete method bodies for all the abstract methods declared within it. Single inheritance of classes versus multiple implementation of interfaces. When building our blueprint hierarchies, we must follow strict rules about how many upper blueprints a single child can extend. While an item can sign as many functional contracts as it needs, it can only ever inherit its core internal data from one single parent blueprint. Restricting blueprints to a single parent prevents severe logical conflicts, while allowing multiple contracts maintains high flexibility. This architectural choice prevents a child blueprint from inheriting conflicting or contradictory internal data from two different parents, while signing multiple empty contracts causes absolutely no conflicts because the child must write all the actual code itself anyway. For example, a student blueprint cannot inherit from both a person blueprint and an employee blueprint because both might have conflicting internal variables for an identification number, but the student blueprint can safely sign one contract to be sortable and another completely separate contract to be printable. The strict limitation that a class can only extend one single superclass is known as single inheritance. While some other programming languages allow multiple inheritance of classes, this often leads to severe naming conflicts known as the diamond problem. To compensate for this structural limitation, Java allows the multiple implementation of interfaces, meaning a single class can implement an arbitrary number of interfaces separated by commas, providing a very safe alternative to multiple inheritance. Marker interfaces. Sometimes we need a way to flag certain blueprints to tell the underlying system that they possess a special property or are allowed to participate in a highly specific system process. We can use completely empty contracts for this purpose, where the mere act of signing the contract serves as a visible tag for the system. Tagging blueprints with empty contracts allows the execution engine to quickly identify and permit special internal operations without requiring the developer to write any complex logic. This tagging system works smoothly because the underlying machine can easily inspect an item during execution to see if it carries the specific tag, and if the tag is present, the machine will automatically enable the special background processing for that item. For instance, if we want to save a student item directly to the hard drive, we can tag the student blueprint with a special empty contract. When the save routine inspects the student item, it sees the tag and automatically converts the student data into a file, whereas it would instantly block the operation and throw an error if the tag were missing. These completely empty contracts are known as marker interfaces. A highly prominent example in the standard library is the serializable interface. It contains absolutely no methods or variables, but when a class explicitly implements it, it signals to the Java virtual machine that objects of this class are officially permitted to be serialized, which is the underlying process of converting the complete state of an object into a byte stream for permanent storage or network transmission. Unified modeling language class diagrams and object relationships. Unified modeling language syntax for classes attributes methods, abstract elements, interfaces, and visibilities. When we plan software, we need a standardized way to draw blueprints of our data structures so that every developer understands them. Drawing these blueprints in a standardized graphical format ensures that the structure of the software is completely unambiguous before any code is actually written. This clarity is achieved because the graphical format uses strict visual rules to divide the blueprint into distinct sections for the name, the stored data, and the available actions, making the entire layout instantly readable. For example, if we design a blueprint for a person, we draw a box and divide it into 3 vertical sections, placing the name of the blueprint at the top, the variables for forename and surname in the middle, and the action to retrieve the name at the bottom. This graphical standard is called the Unified Modeling Language. In these diagrams, a class is represented by a rectangle. The data variables inside are called attributes and the actions are called methods. To specify who can access these elements, we use visibility modifiers, which are drawn as simple signs such as a plus sign for public access, a minus sign for private access, a hash sign for protected access, and a tilde sign for package visibility. If a blueprint or a method is incomplete and must be implemented by a child blueprint, it is called an abstract element and is visually marked in italic text or with the word abstract enclosed in double-angle quotation marks. Pure functional contracts without any implementation are called interfaces and are specifically marked with the word interface in double-angle quotation marks. Associations, directed versus undirected cardinalities, multiplicities, and navigability. Objects in a computer program rarely exist completely alone, as they usually need to interact with other objects to perform complex tasks. Defining the exact connections between different blueprints is essential for understanding how data flows through the entire system. This is because an explicit connection clearly dictates which objects know about each other, and exactly how many objects can participate in a specific relationship, preventing invalid system states. For instance, if we connect a blueprint for a course with a blueprint for a student, we must specify that one course can hold anywhere from 5 to an unlimited number of students, ensuring the course is never completely empty. In the formal diagram language, a structural connection between two classes is called an association, and is drawn as a solid line. The number of allowed objects at each end of the line is called the multiplicity or cardinality, which we write using ranges like 0 to arbitrary many denoted by a star symbol. If the system only needs to find connected objects in one specific direction, we speak of a directed association, which is drawn with an arrow pointing to the target, indicating the navigability. Conversely, if there is no arrow drawn, it is an undirected association, meaning the diagram makes no explicit statement about the navigability, or we simply assume both sides can reach each other. Aggregation part-whole relationship with an open diamond. Sometimes we want to express that a larger object is assembled from several smaller independent objects. Grouping independent objects into a larger assembly allows us to reuse the smaller objects in completely different places within our software. This flexibility exists because the smaller parts maintain their independent lifecycle, meaning they can be freely attached to or detached from the larger assembly without being destroyed. For example, in an online configuration tool, we can assemble a laptop from different processors where a specific processor model exists independently in the database and can be added to hundreds of different laptop configurations. This specific type of part-whole relationship is called an aggregation. In a class diagram, an aggregation is visually represented by a solid line with an empty open diamond shape attached to the class that represents the whole assembly. Because it is a loose relationship, the parts can belong to an arbitrary number of wholes at the same time, meaning we can use any multiplicity at the ends of the connection. Composition existence-dependent part-whole relationship with a filled diamond. In other cases, a larger object consists of smaller parts that are physically or logically bound to it and cannot exist anywhere else. Tying the existence of the smaller parts directly to the larger object ensures that memory is automatically cleaned up and no orphaned parts remain in the system. This strict containment guarantees that the parts are completely dependent on the whole, so if the main object is deleted, the system automatically deletes all its internal components as well. For instance, if we model a physical manufactured laptop containing a very specific physical processor, that processor is permanently built into that exact laptop, and if the laptop is destroyed, the processor is completely destroyed alongside it. This strict existence-dependent part-whole relationship is called a composition. We draw a composition in our diagrams using a solid line with a filled black diamond shape attached to the class that represents the whole. Because of the strict dependency, a part in a composition can belong to exactly one whole, or at most one whole, meaning the multiplicity at the diamond end is strictly restricted to exactly 1 or 0 to 1. Realisation relationships inheritance arrows for classes and interfaces. When we create hierarchies of blueprints, we need to clearly visualize which specific blueprints inherit properties from general blueprints or sign specific functional contracts. Drawing clear inheritance lines makes it immediately obvious to any developer which components share the exact same foundation or guarantee the exact same behavior. This visual mapping is vital because it reveals the entire family tree of the software architecture, allowing developers to see at a glance where properties originate and where they are customized. For example, if we have a general blueprint for a person and a specific blueprint for a student, we draw a distinct line between them to show that the student automatically receives all the name properties of the person without us having to write them down twice. In the diagram standard, we visualize class inheritance using a solid line with an empty closed triangle pointing directly to the parent class, indicating a generalization or specialization. When a class formally agrees to fulfill a pure functional contract, we call this a realization relationship. To draw this realization relationship between a class and an interface, we use a dashed line with the same empty closed triangle pointing to the interface, showing that the class implements the required methods. Exception handling and file work. Class hierarchy of exceptions: throwable, error versus exception. When writing computer programs, things can go wrong during execution. To manage these problems systematically, the system categorizes all possible issues into a structured family tree. Grouping all errors into a strict family tree allows the program to distinguish between minor recoverable issues and catastrophic system failures. This differentiation is crucial because attempting to recover from a catastrophic failure can leave the system in an unstable state, whereas ignoring a minor issue can cause the program to crash unnecessarily. For instance, if a program tries to open a missing text file, it can easily catch this specific file issue and ask the user for a different file name, but if the entire computer runs completely out of memory, the program should instantly shut down because it can no longer function safely. In the Java programming language, the universal parent blueprint for all issues is called Throwable. This parent branches into two main categories, where the first is called error, which represents fatal system problems such as running out of memory that developers should generally not attempt to catch. The second main category is called exception, which represents handleable application problems such as a missing file that the program can and should actively resolve to continue its normal operation. Checked exceptions versus unchecked exceptions and runtime exceptions. Even within the category of handleable problems, there is a further distinction between problems that the programmer must anticipate and problems that happen unexpectedly due to poor programming logic. Forcing developers to explicitly prepare for certain predictable problems ensures that the software remains robust in unpredictable environments. This preparation is necessary because external factors like missing files or dropped network connections are entirely outside the control of the program, so the system must guarantee that a contingency plan exists before the program is even allowed to run. For example, if a developer writes a routine to read a file, the translation tool will absolutely refuse to translate the code into a working program unless the developer explicitly writes a backup plan for the exact scenario where the file cannot be found. Problems that the translation tool forces the developer to handle are called checked exceptions, which include standard input-output exceptions. In contrast, problems that arise from logical mistakes such as trying to access an empty variable are called unchecked exceptions. The base category for these unexpected logical mistakes is called runtime exception, and because they indicate faulty code rather than external environmental issues, the translation tool does not force developers to write explicit backup plans for them. Triggering exceptions using throw and declaration using throws. When a specific part of our program detects that something has gone wrong, it needs a reliable way to immediately stop its current task and alert the rest of the system about the problem. Stopping the current task and loudly announcing the error ensures that invalid data does not silently corrupt the rest of the calculation. This immediate halt is effective because it forces the execution engine to completely abandon the active routine and pass the error backwards up the chain of command until it finds a component that knows how to resolve it. For instance, if a calculation routine expects a positive number but receives text instead, it instantly creates an error object describing the invalid input and tosses it back to the main menu routine, preventing the calculation from producing a mathematically impossible result. The deliberate action of creating an error object and tossing it into the system is performed using the throw keyword followed by the specific exception object. If a method does not handle a checked problem itself, it must explicitly warn its callers that it might produce this problem, which is done by adding the throws keyword to the method signature followed by the type of the exception. This declaration acts as a formal warning contract, forcing any other method that calls it to either handle the problem or declare the warning further up the chain. Catching and handling with try-catch blocks and rules for the order of catch blocks. Once a problem has been announced, the system needs designated safe zones where the program can inspect the error and execute the appropriate recovery steps without crashing. Setting up dedicated zones to test risky code and intercept resulting errors allows the program to gracefully recover from failures. This interception mechanism works smoothly because the system separates the normal successful instructions from the error recovery instructions, making the code much easier to read and ensuring that the recovery steps only run when a specific problem actually occurs. For example, a developer can wrap the instructions for reading a file in a safe zone and attach two separate rescue routines where the first specifically handles the case of a missing file by showing a warning message, and the second handles general reading errors. The safe zone where risky code is executed is called a try block. Directly following this block, we write one or more catch blocks which act as interceptors for the exceptions. Because the system checks these interceptors strictly from top to bottom, developers must always place the catch blocks for highly specific exceptions first, and the catch blocks for more general exceptions last to ensure that the correct and most specific recovery routine is executed. The finally block for safe resource release. When a program opens external elements like files or network connections, it must guarantee that these elements are properly closed and returned to the operating system even if a severe error suddenly interrupts the task. Guaranteeing the execution of a final cleanup routine prevents the system from permanently locking up vital external resources. This absolute guarantee is necessary because an error normally causes the program to instantly jump out of its current routine, which means that any normal cleanup commands written at the end of that routine would be completely skipped and the file would remain locked. For instance, if a program opens a large database file but crashes halfway through reading it, a guaranteed cleanup routine ensures that the close command is still executed, allowing other programs on the computer to access the database file afterwards. To implement this guaranteed cleanup, developers use a finally block which is attached to the very end of a try and catch structure. The execution engine guarantees that the instructions inside the finally block will always be executed regardless of whether the try block finished successfully or an exception was intercepted, making it the perfect and only truly safe place to release operating system resources. The try with resources statement and auto-closable resources from Java 7. Because remembering to manually write cleanup routines for every single file or connection is tedious and prone to human error, modern programming provides an automated way to handle resource management. Automating the cleanup process drastically reduces the risk of resource leaks and makes the program code much shorter and safer. This automation is highly reliable because the translation tool automatically generates all the complex background instructions required to safely close the items the moment they are no longer needed, completely removing the burden from the developer. For example, instead of writing 10 lines of code to carefully open a file, process it, and then manually check if it needs to be closed, the developer simply opens the file inside the declaration of a safe zone, and the system automatically closes the file the exact millisecond the zone is exited. This automated structure, introduced in Java 7, is called the try with resources statement. It works by declaring and opening the resource directly inside the definition of the try block. The system automatically closes any resource declared this way as long as the resource formally signs a specific functional contract known as the auto-closable interface, which guarantees that the item possesses a standard closing method. Basics of file input-output in Java using FileReader and BufferedReader. Working with text documents stored on a computer hard drive requires a structured approach to locate the document, open it, and read its contents efficiently without overwhelming the computer memory. Reading a document chunk by chunk using a temporary memory area is far more efficient than reading it one single letter at a time or loading the entire massive file at once. This staged approach is optimal because accessing the physical hard drive is an extremely slow process, so fetching large chunks of text in a single swift motion and holding them in fast temporary memory drastically speeds up the overall reading process. For instance, if a program needs to process a book containing 1 million words, fetching each letter individually from the hard drive would take minutes, but fetching entire sentences into a fast intermediate memory buffer allows the program to read the book in a fraction of a second. In the Java language, we use a file object to represent the physical path and location of the document on the hard drive. To actually open and read the text, we use a FileReader, which translates the raw computer bytes into readable characters. Because the basic reader is very slow, we wrap it inside a BufferedReader, which provides a temporary intermediate memory area, allowing us to read whole lines of text highly efficiently. Container types and data structures collections. Abstract data types for managing sets of objects. When writing software, we often need to store and manage multiple related items together. Grouping multiple related items into a single managing entity simplifies the development of complex software. This simplification occurs because developers can interact with a large collection of items through a single point of contact without having to manually track every individual piece of data in the computer memory. For example, if we want to store the names of all students attending a specific university course, we can put them into a single managing entity and ask it to count the students rather than creating hundreds of separate variables for each student. In the formal language of computer science, these managing entities are called container types, because we interact with them purely through a specific set of operations without needing to know how they internally store the data. We classify them as abstract data types. The internal data structure is completely hidden from the user, which ensures that the developers of the container can change the underlying storage mechanism without breaking any surrounding application code that relies on it. The stack container last in first out principle push-pop is empty and size. Some storage mechanisms strictly control how we can add or remove items, forcing us to only interact with the item that was added most recently. Restricting access to only the most recently added item is highly useful for software processes that must be reversed exactly step by step. This restriction is effective because it forces the computer to process the most recently interrupted task before it can return to any older suspended tasks, ensuring a strict chronological reversal. For instance, when a computer program calls multiple routines in a sequence, it uses this exact structure to save the local variables so that the last called routine finishes first before the previous routine resumes its execution. This specific container type is called a stack, and it operates strictly on the last in first out principle. To interact with the stack, we use specific operations where the push operation places a new element exactly on the top of the stack, and the pop operation removes and retrieves the uppermost element. Furthermore, we can check if the stack contains any items at all using the isEmpty operation, and we can determine the exact number of elements using the size operation. The queue container first in first out principle enqueue and dequeue. Other storage mechanisms process items strictly in the exact order they arrive so that the oldest items are always handled before the newest ones. Processing items in their exact arrival order ensures fairness and proper sequencing in systems where tasks arrive at unpredictable times. This sequential processing guarantees that no task is unfairly delayed because every new item is forced to wait at the back of the line until all older items have been successfully handled and removed from the front. For example, if a computer program needs to send data to a hardware device, it places the print jobs into this structure so that the first document sent is the first document printed while newer documents wait in sequence. In computer science, this structure is known as a queue container, which strictly enforces the first in first out principle. We add a new item to the back of the queue using the enqueue operation, and we remove and retrieve the oldest item from the very front using the dequeue operation. Just like other containers, the queue provides basic operations to check if it is completely empty and to determine its current size. List container random access and sequential order. Sometimes we need a storage mechanism that keeps items in a specific sequence but still allows us to directly reach into the middle to read or change any item we want. Keeping items in a specific sequence while allowing direct access to any position provides maximum flexibility for handling ordered information. This flexibility arises because the structure assigns a specific numerical position to every single item, allowing the program to target any position directly without having to process all preceding items. For instance, if we have a database of 10 registered users stored in order, we can directly overwrite the data of the 5th user without having to read or modify the data of the first 4 users. This highly flexible container is called a list, which represents an ordered sequence of elements. Because we can retrieve or modify an element at any specific position instantly, the list provides what is known as random access. Unlike restricted structures, we can freely use operations to get insert or remove elements at any given numerical index while the container automatically maintains the underlying sequential order. Set sets without duplicates unordered. There are situations where we need to collect items, but we must absolutely ensure that no item is accidentally stored more than once. Using a storage mechanism that automatically rejects duplicate items is highly efficient for managing distinct unique entities. This automatic rejection is efficient because the programmer never has to write manual checks to search for existing copies before adding new data, saving significant processing time and preventing logical errors. For example, if we want to store the identification numbers of all winning lottery tickets, we use this structure to guarantee that each number appears exactly once even if a user tries to enter the same winning number twice. A container that strictly prevents duplicate entries is called a set. Unlike sequences, a set does not guarantee any specific order of its elements, meaning it is completely unordered and does not support random access by a numerical index. We interact with a set primarily by using the add operation to include an element and the contains operation to quickly check if a specific element is already present in the collection. Map key value mappings and uniqueness of keys. In many programs, we need to look up specific information by using a unique identifier. Linking unique identifiers directly to specific pieces of information creates a highly efficient lookup system. This linkage allows the computer to instantly find the associated data by simply asking for the identifier without having to search through the entire collection item by item. For instance, if we build a university database, we can link a unique student identification number directly to a student record so that providing the number instantly retrieves the correct student details. This lookup structure is called a map, or sometimes a dictionary, because it stores data as key-value pairs. In this relationship, the unique identifier is known as the key, and the associated data is known as the value. The map strictly enforces the uniqueness of keys, meaning that if we use the put operation to add a new value using an already existing key, the map will automatically overwrite the old value with the newly provided one. Data structures for implementations: arrays versus linked lists. Underneath the surface, all these storage containers must be built using fundamental building blocks provided by the computer memory. Choosing the correct fundamental building block heavily influences how fast a container operates and how much memory it consumes. This is because some building blocks reserve one massive continuous chunk of memory which is very fast to read, but hard to resize, whereas other building blocks use small scattered pieces of memory that are easy to expand but slower to read sequentially. For example, if a programmer builds a stack using a continuous block, they must carefully create a brand new larger block and copy all items over when the stack gets full, whereas building it with scattered pieces allows them to seamlessly add new items indefinitely. The fundamental structure that uses a continuous, unfragmented block of memory is called an array, which has a fixed capacity and provides instant access to any position. Conversely, the structure that uses scattered individual pieces of memory is called a linked list. Because an array keeps empty slots, it can waste memory, and if elements are removed, the developer must explicitly clear the reference to prevent a severe issue known as loitering so that the garbage collector can reclaim the space safely. Algorithms on linked lists: inserting nodes, deleting nodes, and traversal. To make a chain of scattered memory pieces work, we have to carefully connect them and write strict instructions to navigate through the chain. Managing a chain of connected pieces requires precise step-by-step instructions to ensure the chain never breaks. This precision is strictly required because the system only knows the location of the very first piece and relies entirely on each piece holding the correct address of the next one to keep the whole structure intact. For instance, if we want to remove the first piece of the chain, we must first safely memorize the location of the second piece before we delete the first one, otherwise the entire rest of the chain will be permanently lost in the computer memory. The scattered pieces of memory in a linked list are formally known as nodes, where each node contains the actual data item and a specific reference pointing to the next node. When inserting nodes at the beginning, we create a new node and point its next reference to the old first node before updating the start of the list. When we want to read all elements, we perform a traversal, which means we use a loop to follow the references from the first node continuously until we hit an empty reference known as null, which indicates the absolute end of the chain. The Java Collections Framework: list, array list, linked list, stack, queue, deque, set, map, hash map. Because programmers need these storage containers in almost every single project, the creators of the programming language have provided a massive built-in library that contains ready-to-use versions of all of them. Relying on the built-in library of containers saves an enormous amount of time and prevents critical programming errors. This reliability is guaranteed because the provided containers have been strictly tested and highly optimized by language experts over many years, ensuring they run perfectly without any extra effort from the user. For example, instead of spending hours writing a custom chain structure to hold text, a developer can simply import the standard sequence container from the library and instantly start adding text elements to it with a single standard command. This comprehensive library is called the Java Collections Framework, which provides standardized interfaces like the list interface, the set interface, and the map interface. For the list interface, the framework offers the array list, which is backed by a continuous array, and the linked list, which uses a chain of nodes. Furthermore, it includes the queue interface for first-in, first-out processing and the deque interface for double-ended queues, while offering highly optimized map implementations such as the hash map, which uses a mathematical hashcode to instantly locate key value pairs. Generic programming. Basic idea and motivation: type safety at compile time and avoidance of typecasts at runtime. When storing data in early software containers, developers had to use a universal storage format that accepted any item, but this meant the system forgot what specific items were stored. Forcing the system to remember the exact type of stored items prevents sudden crashes when the program is actually running. This prevention works because the translation tool can inspect the exact types before the software ever runs and strictly block any attempts to insert or extract the wrong kind of data. For example, if a developer creates a storage stack specifically for text strings, the system will instantly flag an error during translation if they accidentally try to add a numerical value to it, whereas an older universal stack would accept the number and crash later when the program tries to read it as a string. In the formal vocabulary of the Java programming language, the mechanism that allows us to specify exact types for containers is called generic programming. Before this mechanism existed, developers had to manually translate universal objects back into specific objects using a process called typecasting, which often led to a class cast exception at runtime if the translation failed. By defining the exact type in advanced generics provides strict type safety at compile time, completely eliminating the need for these dangerous manual translations during the actual execution of the program. Parametric polymorphism. Sometimes we want to write a general instruction manual for a task that works exactly the same way regardless of the specific materials we are working with. Writing a single universal manual that accepts interchangeable material labels drastically reduces the amount of code we have to write and maintain. This efficiency is achieved because the overall sequence of actions remains completely identical, allowing the computer to simply substitute the placeholder label with the actual required material whenever the task is performed. For instance, the logical steps to add and remove items from a linked stack are exactly the same whether we are stacking person objects or complex numbers, so we only need to write the stacking logic once and simply swap the material label. This concept of writing code with interchangeable type placeholders is known as parametric polymorphism, which is also referred to as universal polymorphism. It contrasts with other forms of flexibility we have seen, such as subtype polymorphism achieved through class inheritance or ad hoc polymorphism achieved through method overloading by allowing a single definition to operate uniformly over an infinite number of different types without rewriting the underlying logic. Syntax of generic classes and interfaces, type parameter T, and naming conventions. To create these flexible blueprints, we need a specific way to tell the computer that certain words in our code are not actual data types but just temporary placeholders that will be defined later. Enclosing these temporary placeholders in special markers right next to the blueprint name clearly separates the fixed structure from the flexible parts. This structural separation guarantees that the translation tool instantly recognizes these placeholders upon reading the first line of the blueprint and correctly applies them throughout all the internal instructions. For example, when defining a flexible storage box, we write the blueprint name followed by a placeholder letter enclosed in markers, and then we use that exact same placeholder letter inside the box whenever we need to declare the type of the stored item. In the formal syntax, we declare these flexible blueprints by writing the class or interface keyword followed by the identifier, and then a list of one or more type parameters enclosed in angle brackets. To maintain readable and standardized code, developers follow strict naming conventions where these type parameters are typically single uppercase letters such as E for elements in a container, K for unique keys, V for values, or simply T for a general type. Generic methods and bounded type parameters. In addition to entire flexible blueprints, we can also write individual flexible actions that accept temporary placeholders just for the duration of that specific action. However, sometimes these actions require the placeholder material to possess certain minimum capabilities to work correctly. Setting strict minimum requirements for the placeholders ensures that our flexible actions can safely perform complex operations on the provided data. This safety is guaranteed because the translation tool will actively block any placeholder that does not fulfill the stated requirements, ensuring that the necessary operations are always available when the action runs. For instance, if we write a flexible mathematical action to add 3 items together, we must explicitly restrict the placeholder to only accept numbers, because if we allowed completely unrestricted placeholders, someone might try to pass in a text string object which cannot be mathematically evaluated. Actions that define their own independent type placeholders are called generic methods, and their type parameters are written in angle brackets just before the return type. When we restrict these placeholders using the extends keyword followed by an upper boundary type, we create bounded type parameters which strictly limit the allowed substitutions to either the boundary type itself or its specific child subtypes. Concepts of type erasure of the Java compiler and bytecode compatibility. Because the flexible placeholder system was added to the programming language many years after its initial release, the creators had to ensure that perfectly working older programs would not break when run on newer systems. Removing all specific placeholder information after the initial translation phase guarantees complete compatibility with older execution environments. This removal strategy works because the translation tool completely verifies all safety rules beforehand and then actively strips the specific type labels away, leaving behind pure universal code that any older machine can effortlessly understand and execute. For example, if a developer writes a flexible list specifically for student objects, the translation tool will rigorously check the types, but the final compiled file will only contain a general list of universal objects looking exactly like a list from the earliest versions of the language. This fundamental design decision in the Java translation tool is known as type erasure. Because of type erasure, generic type information is completely lost after compilation into bytecode, meaning that the Java virtual machine has absolutely no knowledge of the generic parameters at runtime, which unfortunately means that generic containers cannot provide absolute type safety during the actual dynamic execution of the software. Special case arrays restrictions with generics and array type signatures at runtime. Unlike flexible generic containers, the simple continuous memory blocks provided by the fundamental system behave very differently when it comes to remembering what kind of data they hold. Continuous memory blocks strictly memorize their exact data type and actively monitor every single item inserted into them while the program is running. This strict active monitoring occurs because these fundamental blocks do not undergo the removal process during translation, so the execution engine always knows exactly what type of item is permitted and instantly crashes the program if an invalid item is inserted. For instance, if a developer creates a continuous block designed solely for student objects and someone attempts to place a professor object into it, while the program runs, the system will immediately trigger a severe runtime error called an array store exception. These fundamental continuous memory blocks are called arrays, and unlike generics, arrays retain their exact type signature at runtime. Because arrays preserve their type information and generics suffer from type erasure, the two concepts clash fundamentally, leading to severe restrictions where developers are strictly prohibited from creating arrays of generic types. Furthermore, generics only work with complex reference types, meaning primitive data types like simple integers must be wrapped into corresponding object classes using automatic boxing before they can be stored. Variance concepts: covariance, invariance, and contravariance. When we have a specific item that acts as a child of a general item, we must understand how containers or actions involving the child relate to containers or actions involving the parent. Different storage structures and actions follow completely different rules regarding whether they automatically inherit the parent-child relationships of the items they contain. These varying rules exist because some structures perform active safety checks during execution and can therefore allow flexible substitutions, whereas other structures lose their safety information and must rigidly block substitutions to prevent invisible memory corruption. For example, because continuous memory blocks actively check data during execution, an array of students can safely substitute an array of general persons, but a generic list of students can absolutely never substitute a generic list of persons because the generic list cannot defend itself against invalid insertions later on. In the formal vocabulary, the ability of a complex type to maintain the inheritance direction of its component types is called covariance, which applies strictly to Java arrays. The complete refusal to maintain any inheritance relationship whatsoever is called invariance, which strictly applies to all generic types in Java. A reversed inheritance relationship is known as contravariance, and while Java supports covariance for the return types of overridden methods, it does not support contravariance for method parameters, resorting instead to method overloading when parameter types are changed to supertypes. Main Topic 9: Design Patterns. Concept motivation and the Gang of Four catalog. Writing well-structured and easily maintainable software requires significant experience, which is often gained by learning from senior developers. Relying on proven blueprints saves developers from constantly reinventing mechanisms for recurring problems when designing the architecture of a software system. This standardization is highly effective because using established templates ensures that the resulting architecture is robust, easily understandable for other programmers, and free of common design flaws. For example, if a developer needs a reliable way to notify multiple components about a data change, they can look up a documented blueprint for this exact problem rather than designing a flawed notification system from scratch. In the formal vocabulary of object-oriented programming, a documented solution approach for a recurring problem is called a design pattern. The most famous collection of 23 such standard solutions was published in a book by Eric Gamma, Richard Helm, Ralph Johnson, and John Vlissides, who are universally known as the Gang of Four. Their catalog provides abstract descriptions of solutions, including the problem context, the structural elements, and the resulting consequences. Pattern categories: creational, structural, and behavioral. The extensive catalog of standard solutions is systematically divided into three major groups based on what the underlying solutions actually do. Grouping the solutions helps developers quickly find the right blueprint depending on whether they need help building objects, organizing them, or defining their communication. This categorization is useful because it reduces the cognitive load on the programmer, allowing them to instantly narrow down their search to a specific domain of software architecture. For instance, if a programmer is struggling to assemble a complex user interface out of hundreds of small buttons, they will completely ignore the communication blueprints and specifically look into the group which deals with organizing parts into larger assemblies. The standard catalog categorizes these blueprints into creational patterns which deal with the independent creation and assembly of objects. Furthermore, it defines structural patterns which describe the organization of classes and objects into larger structures. Finally, it outlines behavioral patterns which govern the distribution of responsibilities and the complex communication between objects. Creational patterns: singleton, abstract factory, and factory method. Sometimes a software system requires absolute certainty that exactly one single copy of a specific component exists throughout the entire program, while in other cases the system must blindly manufacture families of related parts without knowing their exact blueprints. Controlling the manufacturing process ensures that the system does not accidentally waste memory with duplicate managers or crash by mixing incompatible parts from different manufacturers. This strict control is necessary because creating objects randomly across the entire application leads to chaotic dependencies, whereas centralizing the creation process completely hides the complex initialization steps from the rest of the software. For example, in a kitchen planning software, the system needs one single central manager to coordinate the application, and it needs a specialized manufacturing routine that generates only matching base cabinets and drawers from one specific furniture manufacturer. The pattern ensuring the uniqueness of an instance is called the singleton pattern, which hides its constructor and stores its only object in a class variable, making sure the retrieval action is atomic and thread-safe for concurrent access. When a system needs an interface to create families of related objects without knowing their concrete classes, it uses the abstract factory pattern. Furthermore, the system can use the factory method pattern, which is a creational blueprint that delegates the exact object creation process to subclasses through an abstract method. Structural patterns: adapter and composite. Connecting pre-built software components often fails because their connection points do not match, or because we need to treat a massive group of components exactly the same way as a single individual component. Introducing an intermediate translating component, or establishing a uniform tree structure, allows the system to seamlessly integrate completely foreign parts and handle massive assemblies with a single command. This structural alignment works flawlessly because the system builds a protective shell around incompatible or complex parts, presenting a perfectly standardized face to the outside world while handling all the messy translations internally. For instance, if a kitchen planner needs to connect a foreign oven to a standard cabinet, the developer builds a translator wrapper around the oven. Additionally, to calculate the total price of the kitchen, the developer sends a single calculation command to the main room component, which automatically forwards the command down to every single cabinet and drawer. The pattern that resolves interface incompatibilities is called the adapter pattern, which performs interface adaptation, either as an object adapter using composition, or as a class adapter using multiple inheritance. The pattern that creates hierarchical part-whole structures is called the composite pattern. This pattern defines a uniform component interface, allowing the client program to treat individual leaf objects and complex composite containers exactly the same way. Behavioral patterns: observer strategy and iterator. Objects must frequently react to changes in other parts of the system, dynamically change their own internal logic, while running or systematically hand out their stored data one piece at a time. Decoupling the communication and the algorithms from the core data ensures that the system can add new reactions or swap calculation rules instantly without modifying the original data components. This decoupling is highly reliable because the objects no longer need to know the exact identities of their communication partners or the exact mathematical formulas, allowing them to simply trigger a general update or request a generic calculation. For example, in a cockroach racing application, a betting office component can automatically receive updates whenever a cockroach finishes a race. Meanwhile, the overall ranking list can instantly switch its sorting rule from sorting by time to sorting by name, while a reading component safely pulls one cockroach after another from the list to display them on the screen. The pattern that provides loose coupling by notifying interested objects about state changes is called the observer pattern or publish-subscribe pattern, which separates the monitored subject from its dependent observers. The pattern that encapsulates interchangeable algorithms at runtime is called the strategy pattern, which allows the context to swap its internal calculation logic dynamically. Finally, the pattern enabling sequential traversal through a hidden data structure is called the iterator pattern, which in Java utilizes the iterable interface to generate the traverser and the iterator interface to actually perform the step-by-step access. Graphical user interfaces and model view controller architecture. Architecture of desktop graphical user interfaces and event-driven programming. When we use software on a personal computer, we interact with graphical screens rather than typing text commands. Building these visual screens requires the software to rely on the foundational display capabilities of the underlying operating system. This reliance is necessary because managing the physical screen pixels and windows is highly complex, so the operating system provides a dedicated manager and display server to handle the basic drawing tasks. For example, when a developer writes a desktop application, they do not write instructions to physically light up pixels on the monitor, but instead send a command to the operating system to create a standard window. In software engineering, this visual interaction layer is called a desktop graphical user interface. Because the program must constantly wait for the user to do something like moving the mouse or typing, this approach is known as event-driven programming, where user actions trigger specific software reactions. Java FX Framework Lifecycle of a Java FX application. Creating a modern visual application requires a strict sequence of steps to ensure the software starts, runs, and closes correctly. Following a predetermined startup and shutdown sequence guarantees that all visual elements and background tasks are fully prepared before the user sees anything on the screen. This strict preparation sequence is crucial because attempting to draw a window before the underlying data is ready would cause the application to crash immediately upon startup. For instance, when a user starts a kitchen planner application, the system first loads the available furniture from the hard drive behind the scenes, and only after that is complete does it finally open the main planning window. In the Java FX framework, every visual program must inherit from a foundational class called the application class. The lifecycle begins when the framework calls the launch method, which subsequently triggers the init method for basic setup. After setup, the framework automatically executes the start method, which the developer must provide to actually build the main window, and when the user finally closes the program, the framework calls the stop method to safely shut everything down. Component structure stage scene and the scene graph. Every visual application needs a physical window and a structured way to organize all the individual visible elements inside that window. Organizing visual elements into a strict branching structure makes it possible to manage highly complex user interfaces efficiently. This branching structure works effectively because it establishes a clear hierarchy where moving or hiding a single parent element automatically moves or hides all of its attached child elements, ensuring the display remains perfectly consistent. For example, if a developer groups 3 text input boxes inside a main container and then decides to move the container to the right side of the screen, all 3 input boxes automatically move together with it without needing separate commands. In the framework, the physical window provided by the operating system is called the stage. Inside this window, we place a scene which acts as the absolute top-level container for all content. The hierarchical structure holding all the individual visual nodes is formally known as the scene graph, which consists of a root node at the top, branching nodes in the middle, and individual leaf nodes at the very bottom. Controls and widgets: button, text field, list, view label, and menu bar. Users need concrete visual elements to enter information, trigger actions, and read data provided by the software. Providing standardized interaction elements ensures that users instantly understand how to operate the software without needing instructions. This immediate understanding occurs because people have learned how standard buttons and text boxes look and behave from using other programs, so recognizing these familiar shapes instantly communicates their purpose. For instance, if a university administration program displays a small rectangular box next to the word forename, the user intuitively knows they must click inside the box and type their name using the keyboard. These interactive graphical components are generally referred to as controls or widgets. A button is used to trigger a direct action, while a text field allows the user to type in short text. A list view displays a sequence of selectable items, while a label simply displays uneditable text. Finally, a menu bar provides a horizontal list of menus typically placed at the very top of the application window. Layouts and containers: composite structure, grid pane, V-box, H-box, and border pane. Visual elements must be arranged neatly on the screen so that the application looks organized and remains usable regardless of the window size. Using automated arrangement managers is far superior to manually specifying the exact pixel coordinates of every single element. Automated arrangement is highly advantageous because it dynamically recalculates the positions of all elements whenever the user resizes the window, ensuring that no buttons or text fields are ever cut off or pushed completely out of view. For example, if a user stretches an application window across two massive monitors, the automated manager will instantly spread the internal containers to fill the new empty space, maintaining a perfectly balanced layout. The structural elements responsible for this automated arrangement are called layouts or containers, which implement a composite structure, meaning containers can be endlessly nested inside other containers. A grid pane organizes items into a strict table of rows and columns. A V-box arranges items vertically in a single column, while an H-box arranges them horizontally in a single row. A border pane divides the available space into 5 distinct regions, namely top, bottom, left, right, and center. Event processing: events and event handlers set on action. When a user clicks a mouse or presses a key, the software must detect this exact moment and execute a specific piece of program code in response. Connecting user actions to specific program routines requires a dedicated mechanism that constantly listens for inputs and routes them to the correct destination. This routing mechanism is strictly necessary because the operating system simply reports raw hardware interactions, so the application framework must translate these raw interactions into meaningful software signals and deliver them to the exact visual element the user interacted with. For instance, when a user clicks a submit button, the framework detects the click and immediately fires a specific signal, causing the program to run the saving routine attached to that exact button. The raw interactions triggered by the user are called events. To process these interactions, developers write specific routines known as event handlers, which act as listeners waiting for a specific event to occur. In the Java FX framework, we attach these routines to interactive elements using the set on action method, which binds a specific block of code to the default interaction of the element, such as a simple mouse click. The Model View Controller Architecture: pattern decoupling of data view and control. As visual applications grow larger, the program code for the data, the visual display, and the user interactions often becomes a chaotic, tangled mess. Strictly separating the data from the visual display and the interaction logic makes large software projects dramatically easier to maintain and expand. This strict separation is highly effective because it allows developers to completely change the visual appearance of the software without ever touching or accidentally breaking the underlying mathematical calculations or data storage mechanisms. For example, in a racing game application, a developer can easily swap a simple text-based ranking list for a highly complex three-dimensional graphical chart without altering a single line of the code that actually calculates the race times. This foundational architectural design is known as the Model View Controller pattern. The model represents the pure data and the core business logic, while the view is strictly responsible for presenting the data to the user. The controller acts as the central coordinator, which processes user inputs, updates the model, and tells the view to refresh its display, thereby achieving a clean decoupling of all three distinct software responsibilities. Data binding properties: observable list and extractors for automatic view updating. When the underlying data in a program changes, the visual display must update instantly to reflect the new information without the programmer having to write manual update commands every time. Establishing a direct automatic link between the data and the visual elements completely eliminates the risk of the screen displaying old, outdated information. This automatic synchronization is highly reliable because the data elements actively send a notification the exact millisecond they change, forcing any connected visual elements to immediately fetch and display the newest value. For instance, if the price of an item in a shopping application is reduced in the database, the visual price tag on the screen instantly changes to the new lower number without the user having to manually refresh the page. This active notification capability is achieved using properties which are special variable wrappers that allow other objects to monitor their changes. Connecting a property directly to a visual element is called data binding. When dealing with collections of items, we use an observable list which alerts the interface when items are added or removed, while utilizing an extractor to ensure the list also detects changes to the internal properties of individual items, triggering a fully automatic view update. Declarative Graphical User Interface Description with FXML and Scene Builder. Writing hundreds of lines of program code just to construct the visual appearance of an application is extremely tedious and makes it very difficult to imagine how the final screen will look. Designing the visual interface using a separate descriptive language and a graphical drawing tool drastically accelerates the creation of complex software screens. This separation of design and logic is powerful because it allows a designer to build the interface visually by simply moving elements around on a digital canvas completely independently from the programmer writing the actual background logic. For example, a designer can visually construct a highly detailed login screen with customized colors and precise spacing using a drawing tool and save it to a file which the main program later simply loads and displays on the screen. This declarative approach is implemented using a specific markup language called FXML, which describes the exact structure of the interface as a text document. Instead of writing this text manually, developers use a dedicated visual tool called Scene Builder, which provides a what you see is what you get environment, allowing them to arrange widgets visually while automatically generating the underlying FXML code. Software testing and unit testing. Goals of software testing: error detection versus error correction. Developing software requires checking whether the final product actually does what it is supposed to do. Verifying the correct behavior of a program prevents software from being delivered in a broken state. This verification is absolutely essential because the translation tool can only find structural syntax mistakes but cannot detect logical flaws in the mathematical calculations. For instance, if a developer writes a routine to calculate the maximum of two numbers but accidentally uses a less than sign, the translation tool will compile it perfectly, but the checking process will reveal the mathematical error before the software is released. The formal process of running a piece of software to verify its expected behavior and find differences between the actual state and the required state is called software testing. The specific software component that is currently being examined is formally known as the system under test. When developers write automated checking routines, they focus primarily on error detection to reveal these deviations, whereas the subsequent process of actually fixing the broken code is a separate task known as error correction. Classification in the software development process: the V-model: unit tests, integration tests, and qualification tests. Checking software is not a single massive task at the very end of a project, but rather a continuous process that mirrors the different stages of building the software. Matching the testing stages directly to the design stages ensures that every level of the software architecture is verified appropriately. This layered approach is highly effective because it allows developers to first verify the smallest individual building blocks and then gradually test larger combinations of these blocks until the entire application is verified as a whole. For example, developers first test a single calculation routine, then they test how that routine interacts with a database, and finally they test the complete graphical user interface with a real human user. In software engineering, this structured alignment of development phases and testing phases is commonly represented by the V model. The first and lowest testing level focuses on the smallest functional elements such as individual methods or classes and is known as unit testing. The second level verifies the interaction between multiple connected components or subsystems and is called integration testing. The final level checks the complete application against the original functional requirements, usually through manual user interaction or load testing, and is formally known as qualification testing. Testing approaches: black box tests versus white box tests. When designing checking routines, developers can either look directly at the internal code structure, or they can completely ignore the internal code and only look at the official instruction manual. Creating different checking routines based on these two opposing viewpoints guarantees a much more thorough examination of the software. This dual perspective is necessary because looking only at the code might miss missing features that were requested in the manual, while looking only at the manual might miss hidden logical errors buried deep inside complex internal loops. For instance, a developer can write one check by reading the manual to ensure a calculation handles negative numbers correctly, and another check by reading the internal code to ensure a specific internal error branch is actually executed. The approach where the tester completely ignores the internal source code and solely bases the checks on the functional specification is called black box testing. This specification-based testing focuses heavily on normal inputs and extreme boundary values. Conversely, the approach where the tester actively uses the internal structure of the source code to design the checks is known as white box testing. This structure-oriented testing aims to execute as many different internal paths and branches as possible to ensure the code is thoroughly covered. Unit testing with JUnit 5 test classes, test methods, and assertions. Writing manual checks that print out text to the screen is very tedious and error-prone because the developer has to read every single line to see if the check passed. Automating the verification of expected results saves a massive amount of time and prevents human oversight. This automation works flawlessly because a dedicated tool can run thousands of individual checks in milliseconds and immediately stop and alert the developer the moment a single calculation produces a result that differs from the mathematically expected value. For example, if a check expects a complex addition to return 22, but the routine returns 20, the automated tool instantly flags the exact line of code where the failure occurred. The standard framework used in the Java programming language to automate these checks is called JUnit 5. Developers organize their checks into dedicated templates called test classes which contain individual checking routines known as test methods. Inside these methods, the programmer writes formal claims about the expected outcome which are called assertions. A highly common assertion is assert equals, which takes the expected value as its first parameter and the actual computed value as its second parameter, throwing an immediate error if the two values do not match exactly. Test driver and system under test. Automated checking routines need a central coordinating mechanism to start them, supply them with data, and record their results. Separating the execution mechanism from the actual software being checked keeps the main application completely clean and free of testing instructions. This strict separation guarantees that the testing commands are never accidentally shipped to the final customer, while ensuring that the checks can be executed independently at any time during development. For instance, a developer can write a separate program that feeds 100 random numbers into a sorting routine and records the results without ever modifying the sorting routine itself. The external automated program that executes the individual test cases and reports their success or failure is called a test driver. The specific software component or program that is currently being examined by the test driver is referred to as the system under test. A complete test case consists of the target unit, the specific input parameters, and the expected output values, allowing the test driver to systematically execute the system under test and verify its behavior. Metrics of test coverage: line coverage versus statement coverage. To evaluate how good our checks actually are, we need a way to measure exactly how much of our written code was actually executed during the testing process. Measuring the exact percentage of executed instructions reveals hidden parts of the software that have never been tested at all. This measurement is critical because unexecuted instructions might contain severe logical flaws that will only crash the software later when a customer uses it. For example, if a calculation routine spans 10 instructions but our checks only trigger the first 5, we instantly know that the remaining 5 instructions represent a massive hidden risk. The general concept of measuring the proportion of executed code is called test coverage. The simplest metric is line coverage, which simply counts the percentage of executed text lines, but this is highly dependent on how the developer formats the text. A more precise metric is statement coverage, which measures the exact percentage of executed individual programming instructions. While statement coverage is useful for finding dead unreachable code, it has a very low error detection rate because a single test run might execute every instruction without testing any alternative logical scenarios. Branch coverage. Simply executing every instruction once is not enough because conditional decisions create different routes through the program. Ensuring that every possible decision outcome is tested guarantees a much higher reliability for the software. This thoroughness is achieved because forcing the checks to take both the true and the false route of every decision ensures that no alternative logical path is left unverified. For instance, in a routine that checks if a number is positive or negative, we must write one check that sends a positive number to trigger the first route and another check that sends a negative number to trigger the second route. The coverage metric that requires every single edge in the control flow graph to be executed at least once is called branch coverage. By ensuring that every decision evaluates to both true and false at least once, branch coverage inherently includes full statement coverage while offering a significantly higher error detection rate. This metric is highly effective at finding control flow errors and is generally considered a strong standard for reliable software testing. Path coverage: complete, boundary, interior, and structured. Complex routines often contain multiple decisions in a row, creating a massive number of unique combinations of routes through the program. Testing every single unique combination of decisions provides the absolute highest level of security possible. This extreme level of testing ensures that no specific sequence of events can crash the program, even if the individual decisions work fine on their own. For example, if a routine has 2 sequential decisions, there are 4 unique routes through the routine, and testing all 4 guarantees that the routine will never fail regardless of the input. The metric that measures the proportion of completely executed unique routes through the entire control flow graph is called path coverage. Because loops can theoretically create an infinite number of routes, complete path coverage is often impossible to achieve. To solve this, developers use boundary interior path coverage, which limits the testing of loops to exactly 0, 1, or 2 iterations. Alternatively, they can use structured path coverage, which strictly limits loop iterations to a specific predefined number, making the testing process mathematically finite and achievable. Condition coverage: atomic multiple condition and minimal multiple coverage. Sometimes a single decision in a program is made up of multiple smaller logical checks combined together. Verifying each individual small check independently ensures that the overall complex decision is perfectly stable. This granular verification is necessary because a complex decision might evaluate to true overall even if one of its internal small checks contains a severe logical flaw. For instance, if a program grants access when a user has a valid password and a valid security token, we must test the password check and the token check independently to ensure both security layers actually work. The metric that focuses on the internal logical components of a decision is called condition coverage. In atomic condition coverage, every single subcondition must evaluate to true and false at least once. In multiple condition coverage, every single possible combination of true and false for all subconditions must be explicitly tested, which requires a massive amount of effort. To balance effort and safety, developers often use minimal multiple coverage, where both the individual atomic conditions and the overall combined condition must evaluate to true and false at least once. Specification-based testing: preconditions, postconditions, exceptions, and side effects. Before we write checks based on the manual, we must understand exactly what the manual promises and what it demands from the user. Defining strict rules for inputs and outputs creates a solid legal contract between the software and the developer using it. This contractual approach works smoothly because it explicitly states what happens when the rules are followed and exactly what errors are produced when the rules are broken. For example, the manual for a division routine strictly demands that the second number is not 0 and promises to return the mathematical quotient, while explicitly stating that it will throw a severe error if a 0 is provided. When performing specification-based testing, developers analyze several formal elements of the application programming interface. They check the preconditions, which are the strict requirements for the input parameters. They verify the postconditions, which are the guaranteed properties of the returned results. They must also test the explicit error cases known as exceptions, which occur when preconditions are violated. Finally, they must verify if the routine produces any side effects, which means checking whether the routine secretly alters any internal data or modifies the provided input objects during its execution. Application Programming Interface Documentation with Java Doc. To ensure that everyone understands the strict rules of a software component, developers need a standardized way to write the manual directly inside the program text. Keeping the manual directly attached to the code ensures that the documentation is never lost and is always updated alongside the logic. This integration is highly beneficial because specialized tools can automatically extract these text blocks and generate beautiful, easily readable web pages that describe the entire software system perfectly. For instance, a developer can write a specific text block above a calculation routine explaining its parameters, and another developer can instantly read that explanation on a generated website without ever looking at the raw code. The standardized format for documenting application programming interfaces in the Java language is called Java Document. Developers write these multi-line comments directly above their classes and methods using special directives marked by the @ symbol, such as param for input parameters, return for output values, and throws for expected exceptions. A dedicated tool can then automatically translate these structural comments into connected hypertext markup language documents, making the complete functional specification easily accessible to all programmers on the team.